Hello everyone, welcome to another recitation video. In this video we're going to go over examples from chapter 10. So we're going to be covering correlation analysis as well as linear regression. And with that we can look at our first example. Alright, so in this example we're going to be looking at a study that's trying to uncover the relationship between BMI and systolic blood pressure. We have a sample of 10 males, 50 years of age, and we have measurements for their weights, heights, and systolic blood pressures. The study has converted their weight and height into one variable called BMI, and we're going to be using that as the independent variable, and then we're going to be using SBP, or systolic blood pressure, as the dependent outcome. Alright, so jumping over to SAS, we begin by using that options command that we had started using in the last chapter, and then after that we're going to, as always, start by importing our data. We're going to use the input function to bring in the variables BMI and SHP. Then we're going to call data lines and then paste in our data. Then we can go ahead and run this to assure that our data is being imported correctly. So hit run, make sure everything looks good, and then we can navigate back over to our code and begin the analysis. Alright, so we can start off by creating a scatter plot to help visualize the data first. So in SAS, creating a scatter plot is a bit tricky because there's differences between the full version of SAS and SAS University Edition. So the main difference between the two versions is the function used to construct the scatter plot. In SAS University Edition, we use function sgplot. In the full version, you can go with the function gplot. And since I'm using SAS University Edition, I'm going to continue with the sgplot function. However, in the description of this video, I'll post the code for the gplot function for those who are using the full version of SAS. So to start constructing the scatter plot, we start off with the proc sgplot, then we specify our data. In the next line, we use option scatter to indicate that we want a scatter plot. We then use x equals and y equals to specify our respective variables. We then use a / in order to begin specifying specific options that we want for our plot. The first option we specify is marker ATTRS, which I believe is short for marker attributes. Then using parentheses, we denote symbol equals circle filled in order to have filled circle markers as opposed to the default, which is just an outline of a circle. Our next line gives us specifics about our x-axis. We use option values equals, then in parentheses use to and by to specify the range and step interval respectively. We conclude with option minor to plot ticks in between our predefined intervals on the axis. And like the x-axis, we use similar code on the following line to specify options for our y-axis. Then finally, close off the code with a run statement and highlight and run to view the scatter plot. So we can make some observations about the scatter plot. The scatter plot looks fairly linear. It looks as if when BMI increases, so too does SBP. However, also there's some departures from that linear trend, but as a whole it looks as if there's a fairly strong positive association between BMI and SBP. Up next, we can formally analyze the correlation by using the proc core command. We use option COV to obtain the covariance matrix. Then we specify our dataset. On the next line, we define which variables are to be analyzed. Finally, we finish it with a run statement. Running proc core, we'll see some interesting results, first of which is the covariance matrix. You'll notice that the diagonal of the matrix is the variance for both BMI and SBP. Then the other two entries in the matrix is the covariance for BMI and SBP. Beneath the covariance matrix, we see some summary statistics that are typical of functions like proc means and proc core, but the most important results are featured in the table below. In this table, we have the correlation coefficients for our variables. Obviously, the correlation between a variable and itself will be 1, but the important results are the correlation coefficients that are not on the main diagonal. Here we see an estimated correlation of 0.86 using Pearson's method, and then below the estimate is the corresponding p-value. Here it's below 0.05, so we have significant evidence to support that the two variables are in fact correlated. The results of the analysis not only concluded that the two variables are correlated, but since the estimated correlation coefficient is 0.86, that means that there's a strong positive linear association between the two variables. So next, Let's take it a step further and run a regression analysis on the data. We start by using the proc reg, then specifying our data. We construct a model using the model argument and then defining SBP as the response and BMI as the explanatory variable, and then we conclude it with a run statement. So running the code brings us to the results tab where we can decipher the output. The first table is the ANOVA table. In this context, we're testing the overall fit of the model. We're comparing our specified model with BMI as an explanatory variable against a model with no explanatory variable. We see a p-value of below 0.05, so we can conclude that our model is in fact significant. The next table in the output reports additional important regression information. Of note is the r-squared value. Here we see a value of 0.74. That means that 74% of the variation of SBP is explained by the body mass index. The final table is the results of the linear regression analysis. The table reports the parameter estimates, their standard error, t-values, and p-values. If we first look at the intercept, we see that the parameter estimate is 40.78. That is the estimated SBP when BMI is 0, which isn't necessarily very meaningful in this scenario. However, we can look at the estimate for BMI. Here we see a value of 3.6. That's to say that with 1 unit increase of BMI results in a 3.6 increase in blood pressure. If we look at the p-value associated with BMI, we see that it is below 0.05. We can conclude that BMI is significant and the beta associated with BMI is not 0. As a matter of fact, the p-value found here is the same p-value found in the ANOVA table. This result isn't an accident, as the f-test is equivalent to a t-test for beta 1 when performing a two-tailed test with a simple linear regression model. Following the analysis, we can see many different diagnostic plots for our regression model. The first row here helps diagnose outliers. Looking at the second plot, we see the studentized residuals. Here, points that exist outside the -2 to 2 band are considered outliers. So here we have one noticeable outlier, and next is the QQ plot. Here the data looks relatively normal and doesn't depart too far from that ideal linear trend line. Scrolling down a bit more, we again see the residual plot, and if we continue further, we see a plot featuring our fitted model along with the corresponding 95% confidence interval and prediction limits. So that actually concludes the analysis for this example. However, we can actually take it a step further and look at the same data set, except this time we'll include another explanatory variable. So if we look at the next example, we have the same data set as before. However, this time we're analyzing the response variable SBT as predicted by both BMI and the number of hours of vigorous exercise. So like always, we can start by importing our data. This time we're using variables exercise, BMI, and SBP. Then we're going to paste in our data, and then we can run the code just to make sure that the data is importing correctly. And since everything looks good, we can start modeling our data. First, we're going to run a regression model using both explanatory variables. So we're going to use the proc reg again with our new data set. We then specify the model. This time, SBP remains on the left, and on the right side of the equal sign, we have both BMI and exercise. And once we specify the model, we can end it with a run statement. So unlike the last example, now we have both exercise and BMI being used to explain the changes in the response variable. And so right away we see the ANOVA table. In this context, though still testing for goodness of fit, the analysis is significantly different than the prior example. Because we're no longer looking at the simple linear regression model, the results are not the same as the analysis in the parameter estimates table. In this case, the ANOVA analysis is comparing both explanatory variables simultaneously. So that's to say that the null hypothesis is that beta 1 and beta 2 are equal to 0, and the alternative is that at least one of them is not 0. Then if we look at the p-value, we see that the results are significant, and with that we reject the null hypothesis, which means at least one of the betas is significant. With that said, we can navigate to the parameter estimates table to research further. Here we see the estimated values for the intercept, BMI, and exercise. The intercept in this case doesn't mean much realistically, however the estimates for the predictors are meaningful. Looking at the estimate for BMI, for example, we see a value of 2.71. This implies that if we hold exercise constant and increase the BMI 1 unit, we'll see an increase of 2.7 units for the SBP. If we look at the p-value for this estimate, this p-value is associated with the hypothesis test that beta 1 is equal to 0 for the null hypothesis and beta 1 does not equal 0 for the alternative. We see that the p-value is below 0.05, so we can claim that the estimate is significant and beta 1 is not 0. On the other hand, we see that the p-value for exercise is greater than 0.05. Thus, we don't have enough evidence to reject the null hypothesis, so we cannot conclude that the beta coefficient is not equal to 0. So now we can look at the diagnostic plots. Again, we see that the outlier from last time is again present, and again, this time the QQ plot looks linear, implying normality. So next, let's model the explanatory variables individually, and then for the sake of completeness, we'll just rerun that model from the first example. So obviously we're going to see the same results as last time, but make note that BMI is significant in this model as well as the multiple regression model that we had just run. And then just to reiterate, BMI is significant because the p-value in the parameter estimates table is less than 0.05. Thus, we can reject the null hypothesis that beta 1 is equal to 0. Therefore, we can conclude that beta 1 does not equal 0. And then as we scroll down, we will again see the same plots that we had discussed in the earlier example. So up next, we can model for exercise exclusively using very similar code as the BMI model, just swapping the variables in the second line. So when we go ahead and run the analysis, right away we're going to see results that are a bit surprising. As you can see from the p-values associated with the ANOVA and the t-test, in this model, exercise is significant because the p-values are well below 0.05. So again, we can look at the diagnostic plots. We see that there actually aren't any super dramatic outliers. There does exist one observation on the cusp, however. When looking at the QQ plot, the residuals look fairly linear, which implies normality. So with a seemingly contradicting result, we can question how exercise can be significant in one model and insignificant in another. One way to answer this is maybe to look at the correlation matrix. So now we use proc core once again. This time we select all three variables. Running proc core yields some very interesting results. If we look at the Pearson correlation table, we can see the correlation test for our selected variables. Of note, the correlation between BMI and SBP is significant, as well as the correlation between exercise and SBP. However, most importantly, the correlation between exercise and BMI is also significant. This correlation that exists between our explanatory variables could cause some issues for our model. Having highly correlated regression variables can impact the ability to estimate regression coefficients, which may be the reason why we saw these seemingly paradoxical results in our different models. So that actually wraps up the examples for Chapter 10. If you have any questions, please reach out and feel free to drop by on my office hours. Thank you for watching.